Hello, today we're going to do a review of the electromagnetic spectrum, what EM radiation is, and an overview of a spectroscopy and the different types and how it can tell us about the molecules or the atoms that we're looking at. Okay, so this should be a review from chemistry and probably back from P's or algebra-based physics, depending on which course you took your freshman year. Okay, so electromagnetic radiation is just the radiation that we get from light. Okay, so we often think of light as being just the visible spectrum, the colors of the rainbow, for example, but electromagnetic radiation has a really wide range of energies and frequencies and wavelengths, and we can only see just a fraction of it. But all of it we can describe as waves, okay? So things that have a long wavelength, as shown here, they do have a low frequency. So if the wavelength is long, we can't get as many waves through in a given amount of time, and the frequency is just the number of waves per second. So if the wavelengths are shorter, we get more waves per second, okay? So we have an equation to relate these two things. Lambda is our wavelength. Okay, that's a Greek letter. It looks kind of like an upside down Y. Okay, and it is equal to the speed of light, which is the same for all kinds of light. Okay, so the wavelength and the frequency will change depending on what kind of light it is, but the speed of the light is the same no matter what kind of light it is. Okay, and that value is 3 times 10 to the 8th meters per second. Okay, that value is given on your equation sheet, so you don't need to memorize it. And this equation is also given on your equation sheet, but you need to be able to know how to use it. So the wavelength is equal to the speed of light divided by the frequency, which is how many waves we get per second. Okay, so let's do an example, a couple of examples using this equation. So if we have a cell phone that has a frequency of 815 megahertz, and we want to know what the wavelength of the frequency is. So, first thing we need to do is convert megahertz into hertz, okay? I did not ask you to memorize all of the prefixes, but there are some cases where you need to know how to use them, so it would be good to review them because they may, I'm not going to test you on that specific scale, but you might need to put them into different units. So mega, the big M, that means like a lot of hertz. So there are 10 to the 6 hertz in 1 megahertz. Okay, so 815 megahertz is equal to 815 times 10 to the 6 hertz. And a hertz is the same as this, is the same unit as per second. So you can use them interchangeably. Okay, so using our equation from the previous slide, we have lambda, which is the wavelength, which is what we're trying to find, is equal to the speed of light, divided by the frequency in hertz, okay? And so if we do that math out, then we end up with 0.368 meters, okay? So this is actually a pretty long frequency, which makes sense because the higher the frequency gets, the more dangerous the light is, or the radiation is to us. And since we use cell phones every day, it makes sense that those would have very long wavelength or relatively small frequencies. Okay. The second question is X-rays utilized in medical imaging typically have a wavelength around 0.25 nanometers. Okay, so a nanometer, that's another one of those prefixes, is a very small distance measurement. So 1 nanometer is 10 to the minus 9th meters. So 0.25 nanometers is going to be 0.25 times 10 to the minus 9th. Okay, and then we're going to rearrange our equation. Oh, let me move myself out of the way. We'll need to rearrange the equation because now we have our known value is here on the left. That's our wavelength, and that's going to be equal to the speed of light divided by the frequency. So when we rearrange that, we get that our frequency is 3 times 10 to the 8th divided by our wavelength, which is 0.25 times 10 to the minus 9th, and we get a frequency of 1.2 times 10 to the 18th hertz. Okay. Now, the electromagnetic spectrum. I already mentioned this briefly, but the spectrum is just all of the different wavelengths or energies or frequencies of light that we could, or that we do observe in the universe. it would be a good idea if you have a sense of which things are higher or lower in energy, because it just helps you get a sense of what we're doing when we talk about the electromagnetic spectrum. So for reference, visible light is what most students have some knowledge of, okay, because it's what we see. But if you notice, it's a really tiny portion of the whole spectrum. Okay, higher in energy than visible light is UV light. Okay, think of UV light can give us sunburn. Okay, and so it's slightly higher in energy than the violet light in the visible spectrum. On the other side, the red is the lowest energy visible light that we can see, and infrared, which we can use for like heating food or for heat vision to find people, because we generate heat. That's infrared. So that is in that same, it's close to the visible, but it's just a little bit lower in energy. Microwaves are what we use to heat up our food. So obviously that takes some energy, but we don't want too much energy or they would be dangerous, right? And then radio frequency, that's where our cell phones fall, and it's where like the radio, your TV signals, all that kind of stuff is in the radio range. So we consider that low energy and relatively safe. Okay, and then on the other side of ultraviolet, we have X-ray. That's how we take images of our bones and stuff. So you know that you don't want X-rays too often because they can be damaging to your cells, but in small amounts, not too bad. And then gamma rays are the highest energy. Those would be the most damaging types of light or types of radiation from the electromagnetic spectrum. All right, so I have now so far only talked about light in terms of waves, but we know that light can also behave like a particle, and we call it a photon when we're describing it that way. It is the same energy, it is the same light, but there's just two different ways that we can describe it. So we have also equations to do that. Again, these are on your equation sheet. You don't need to memorize them. H is Planck's constant, and it's also given on your sheet, okay? So we can use that equation to do examples as well. So how much energy is in a photon of green light that has a wavelength of 550 nanometers? Right, so again, we need to convert nanometers to meters, so that's 10 to the minus 9th. Nano and 9 sound similar, so maybe that can help you remember that it's 10 to the minus 9th, okay? And then if we plug that into our equation for energy, we take Planck's constant, which is here, the speed of light, okay, because we need the speed of light if we're using wavelength, which is our lambda, we'll need this equation, and then our wavelength, which is 550 times 10 to the minus 9. Okay, so then you just put that into your calculator, and you get 3.6 times 10 to the minus 19th joules, all right? And that has two significant figures because our 550 only has two significant figures, because we don't know if that 0 is significant or not. All right, so now let's talk about spectroscopy. What can we do with these different types of radiation, and how can it tell us about molecules? So spectroscopy is basically just using that electromagnetic spectrum to learn about a particular sample that has molecules in it. Okay, so the one you're probably familiar with are spectroscopy in the visible or ultraviolet range, and that's where we see electronic transitions. Okay, so if you did the flame lab back in 9th grade or in chemistry, or if you looked at discharge lamps, in each of those cases, what's happening is light is going in that causes electrons to be excited from the ground state to an excited state, and then when they fall back down, we get an emission of light, and that is generally in the ultraviolet or visible range, okay? That takes quite a bit of energy, so of the three types of spectroscopy we're going to talk about, this is the one that's highest in energy. Okay, infrared is slightly lower in energy than the visible light, okay, and that type of spectroscopy can tell us about molecular vibration. So a particular frequency of light can cause the bonds in a molecule to vibrate, okay, and having the bonds vibrate like that doesn't take as much energy as moving the electrons to an excited state, but it does take more energy than just rotating the molecules, okay? So rotations are what we get when we when we emit the sample with microwaves, okay? So if we use radiation in that energy range, that's the same technology that causes things to get warm in your microwave at home. So it's not an accident that those have the same name. Your microwave is set to give just the right amount of energy to cause molecules of water to rotate. Okay, and almost all of our food has water in it. So the rotation of water molecules causes friction in your food and causes it to warm up. So that's really all that a microwave does. So we are not going to do infrared and microwave spectroscopy in the lab, but you can think about microwave anytime you heat up your leftovers at home, right? But we will do visible and UV spectra in the lab. All right, so let's just review basically some terminology for electronic transitions. So I already mentioned the words ground state and excited state. Ground state is going to be the lowest energy state for an atom, for the electron in an atom, all right? And it's going to be where the electron is closest to the nucleus, right? Because that electron is attracted to the positive charge, and closest to the nucleus would be your ground state. And then an excited state would be any state higher in energy than that. So we can have lots of excited states, but there's only one ground state for a particular atom or molecule. Okay, so if we absorb energy, so if we shoot visible or UV light at the atom, and it's the right energy, then the electrons can move from low to high, and that is called absorption because it's absorbing energy. If then that electron is at a high energy state, all right, things always move back to lower potential energy. So as it moves back down, here it's just moving to the second energy level, but it could move all the way down to 1. Then we get that light, or that energy released as light, which sometimes we can see depending on what the separation for our energy levels is. And that is called emission. Okay, so we cannot see absorption with our naked eye, but we can see emission. We can use a spectrometer to measure absorbance. And so with technology and equipment in the lab, we can visualize absorption spectroscopy, but we can't see it with our naked eye. All right, so just to review, if we have a hydrogen atom, remember hydrogen just has one electron, so it's the easiest, simplest example. If we go from n equals 3 to n equals 1, we're going from high to low, and so that's going to release energy, and so that would be an example of emission. If we're going from 1 up to 4, that's going to require energy, and so that would be an example of absorption. Going from 1 to 2, also going up in energy, would be absorption. And if we're going from 5 back down to 2, that would be an example of an emission because we're going from high to low, and so energy would be released. All right, so another example here. We've talked about 3 different kinds of spectroscopy where we give just enough energy for either bonds to rotate, or a little bit more for the bonds to vibrate, or a little bit more for electrons to make transitions within the atom. But it's also possible to give enough energy that we end up ejecting the electron completely or breaking a bond, okay? So anything higher in energy than that would cause our molecules to fall apart or cause an ionization to happen. So here we have ozone, which is O3, breaking down into O2 and just an atom of oxygen. So this problem tells us that the minimum energy needed to break an oxygen-oxygen bond in ozone is 387 kilojoules per mole. So it wants to know, does a photon with a frequency of 1 times 10 to the 15th per second, which is the same as a hertz, have enough energy to break this bond? Okay, so we have to do 2 things. We have to figure out how much energy are we going to need to break one bond, because this is kilojoules per mole. And we also have to figure out how much energy is in one photon that has this frequency. So let's do that first part first. So if we have E equals h nu, that's our equation for finding the frequency, finding the energy using the frequency. So we'll do Planck's constant times our frequency, which is already in hertz, and that gives us a value of 6.626 times 10 to the minus 19th joules, which seems really small, right? But this number here is how much energy we need for a mole of oxygen, or a mole of O3. Okay, so let's figure out how much, one, we need to get from kilojoules into joules, and also how much energy that would be for one molecule instead of a whole mole of them. Okay, so 387 kilojoules per mole. First, we'll do 1,000 joules is 1 kilojoule. okay? And then we know that 1 mole is 6.02 times 10 to the 23rd bonds, okay? So that's a lot of bonds. So in order to just break one bond, we would need 6.43 times 10 to the minus 19th joules. And I just did that by doing the math up here, okay? So now if we compare these two, this number is actually smaller than that number. So that means our photon should have enough energy to break this bond, okay? And it also means that then we'd have like a little bit of energy left over, okay? So for these, you don't need an exact amount of energy, you just need enough. All right, so then our last topic today is Beer's law, okay? So we call it Beer's law for short. The long name is the Beer-Lambert law. And the Beer-Lambert law basically just compares absorbance, which is capital A. Remember I said we could use equipment in lab to measure absorbance. And it relates it to a constant called molar absorptivity that is different for every substance, and you would need to measure it in the lab or look it up in a table of standards, okay? The path length, okay, so the more of the sample you go through, the more absorbance you will have, right? So if it's a really thin sample, then it would not absorb as much, and if it was a really thick sample, it's going to absorb a lot more. And then it's also related to the concentration. So the more concentrated our sample is, the more stuff is going to be absorbed. Right? So we are going to do this in the lab and do some examples. This equation also is given in on your equation sheet, so you do not need to memorize it, but you do need to know how to use it.